One of the key building blocks in MobileNets architectures is factorized convolutions. So in general, factorization is basically an approach that allows to replace standard convolutions with faster versions. And of course, this is not one method or one technique. There are many methods and many techniques, but the technique I'm going to discuss in this video is called Depthwise Separable Convolution. And this Depthwise Separable Convolution is used as a building block in MobileNets architectures. So a little bit of history. The first one who invented this, his name is Laurent Siffre. He was a PhD student, so he published this in 2014 in his thesis. And later, in 2017, a group of scientists in Google have used this Depthwise Separable Convolution as a building block to create a new class or a new family of CNNs that is called MobileNets. And this building block, this Depthwise Separable Convolution, is used both in version 1 and in version 2. So it's an important building block, and this is what I'm going to discuss in this video. For this purpose, I will talk about 4 major points. So the first, here are the outlines. First, I will talk about the main idea. Then, how does Depthwise Separable Convolution work? Afterwards, I will talk about the cost or the computational cost of Depthwise Separable Convolution and a comparison with standard convolution. And finally, I will discuss what makes the Depthwise Separable Convolution work well, or rather, why does it work? So these are the 4 outlines of this video. So to understand the main idea, let's consider a standard convolutional kernel. So let's consider the following kernel. Let's say that I have a kernel K that has the following dimensions. So it has dk times m times n. So this is the height, width, and depth of each kernel, and n is the number of kernels. So this is a convolutional step or convolutional layers, standard convolution. So at the input we have f and its dimensions are df, df, m. And at the output we get j, and the dimensions of j are df times df times n. And of course, we assume that at this convolutional layer we have a stride of 1. This is why we get df, df. This is why we get df, df, but we also should have same convolutions, which requires padding. So this is something that I talked about in the previous video. Right? So what I want to do now is to replace this with a depthwise separable convolution, but we need first to understand the main idea. So here, each kernel in this convolutional layer is a 3-dimensional kernel. So a given kernel ki, such that I starts from 1 up to n, is a 3-dimensional kernel, like that. So basically what this kernel does is that it filters or creates new features by a filter in 3 dimensions. The first dimension is height, second is width, and the third is the depth or the direction of channels. Right? So what we are going to do, or what depthwise separable convolution does, is that this is assumed to be almost equivalent to 2 kernels. So the first kernel is a 2-dimensional kernel. So you can already see that this kernel here is much smaller, could be much smaller than this kernel, especially if m is very high. But we need to filter the depth dimension as well, because this kernel here filters the spatial dimensions only, it filters the height and width. So we need another kernel which filters the depth dimension. So the size of this kernel is dk 1, and this is 1, 1, n. So when we filter with these kernels, we are talking about depthwise convolution. So do not confuse this term, depthwise convolution, with depthwise separable convolution. It's not the same thing. Depthwise separable convolution is means that we are filtering with these 2 kernels, right? But depthwise convolution without the term separable means that we are using just this 3 by 3, or rather dk by 1 kernels. So this step is called depthwise convolution, and this step here is called pointwise convolution, and sometimes, or in the original paper, it's called 1 by 1 convolution. And the reason why it's called pointwise is because if we see the kernel from this angle, then we would see just a point, 1 by 1. So we can say that these 2 kernels basically do the same thing, because this filters the spatial dimensions and this filters the width dimension, which is exactly what this kernel does. But this is useful because it requires less weights, and therefore its computational cost is smaller. So we'll talk later about the computational cost. Now let's see this in action. How can we replace this convolutional layer with these 2 kernels? So the first step is that we take, so this is the depthwise separable convolution. So the first step is to take f, the input f, which have m channels and use these 2-dimensional kernels to filter each channel. So each of these kernels each channel would be filtered by 1 2-dimensional kernel, like that. So this is the first 2-dimensional kernel, filters the first channel. Second 2-dimensional kernel filters the second channel, and the nth dimensional kernel filters the nth channel. What does that mean? It means that the depthwise convolution would have the following convolutional kernel, which is a 4-dimensional or rank 4 tensor. Let's call it K1, with size, or with the dimensions dk times 1, and the number of kernels is m, because we have m channels, so we need 1 kernel per channel. Therefore the number of these 2-dimensional kernels is m. Afterwards we get an output which has the same spatial dimensions and also the depth as the input, because we have a stride of 1 and same convolution with padding. So this output that we get would be filtered by one by one convolutions or one by one kernels. So we can say that the second convolutional layer, pointwise convolution, would have the following kernel. So let's call it K2, and its dimensions are 1 times 1 times, so here the depth of each kernel should span over the entire input, and since the depth of this input is m, then the depth of each one by one kernel should be m, right? So this should be m, and this means that this is wrong. This is not n, this is m. I apologize for that. Now, what is the number of these one by one kernels? The number should be n, because the depth of the output we have here is n. So to get this depth, we need n kernels. And in this way, we would get an output j that has the same dimensions as this output here that corresponds to standard convolutions. We get the output here.